Okay, everybody still awake after lunch? It's a good exciting presentation, right? I'm still me, but I will be talking in this presentation on domain-specific modeling, which I foreshadowed a bit in my earlier presentation. So one of the first things to ask is, what is domain-specific modeling? So let's get that out of the way. Starting first with what it isn't. So a general purpose modeling language is one that's broadly applicable for all kinds of modeling, not surprisingly. A domain-specific modeling language is specific to a specific domain, specialized to a specific domain. What is a domain? Well, it could be, say, for aerospace, it could be specifically for modeling control or electrical systems, an engineering domain, or for some other purpose, specialized for specific organizational processes, some specific project. So it is a constrained modeling language for specific domain or purpose. And domain-specific modeling is systematically modeling using DSMLs for various facets of your system. And sometimes it means using different DSMLs for different facets of your system. But I'm going to add an or in here. Or you can do the same thing by systematically adapting a general purpose language to model in different domains. That is a common way to do it in the domain-specific programming language community, and it is also a common thing to be done in especially the UML and especially the SysML v1 communities, and I want to talk about how we do that in v2. So let's talk about domain-specific modeling in SysML. SysML, we're going to, for this purpose, consider a general purpose modeling language for systems modeling. Now, domain-specific is actually a relative term. You know, you could consider that being specific for systems engineering is itself kind of domain-specific, but I think most people will consider SysML to be fairly general purpose. In SysML v1, further adaptation was done for domain-specific modeling using profiles, very widely used. And the basic idea there is that you adapt specific v1 elements for domain-specific concepts by tagging them with stereotypes, and then tools can key off the stereotypes to provide domain-specific visualization, validation, analysis, whatnot, make it act more like a domain-specific modeling language. And as I said, this is kind of relative because we know SysML v1 was itself defined as a profile of UML. And so very trivially, right, you could define a vehicle as a generic UML class, but in v2, we tag that with a stereotype and it's a block. But stereotypes in that way are really, as I said, just syntactic markers. There's no formal specification of semantics. Now, UML and SysML v2 mostly didn't have formal specifications of semantics anyway. So when you added a profile, it was generally just informal. But even when formal semantics were added, like for foundational UML and other executable UML, or added to SysML 1.7, there really was not a mechanism to further extend those semantics in any easy way if you defined your own profile. So that's where we were at the v1. How are we going to do it in v2? So Sandy showed this morning this diagram, we have shown a lot. On the right, the stack on the right here is syntactic. The fact that it's built up in layers isn't critical, but the main idea is that this is a fairly typical way to define an OMG modeling language using an abstract syntax defined in the meta-object framework. What really makes this architecture new and exciting is the part on the right here. This is the left, that's the right, which is how we define the semantics. So the way the semantics is defined in this architecture is it keys off this core, which has direct semantics and formal logic. But everything else is built using semantic libraries in the language itself. So the kernel semantics of kernel, the kernel modeling language, are actually defined in kernel. They, at the core, reflect back to this formal logic. But when you build things like classes, associations, connectors, the semantics of that is actually all defined in kernel itself, including the semantics of time, relationship, and space. The semantics of SysML v2 is built on that. And basically what SysML v2 is adds an ontological terminology for systems engineering modeling, and then pulls in the semantic details from kernel. By intent, the idea is we can then go a step further and create domain model libraries. Those domain model libraries build on the semantic libraries for the languages to provide domain-specific concepts. How can we use that then to really create a concept of a domain-specific language with actual semantics? So to understand how we do that, let's talk a little bit more about how that semantic stack works for defining SysML v2 itself. So this is a really simple SysML v2 model, right? SysML v2, Sandy showed a lot more complicated models. So I'm going to keep this simple. We just have here a car, part definition for a car. And you notice this looks like a stereotype. You may have noticed that in the earlier SysML v2 notation. It is not a stereotype, it is a keyword that identifies the kind of thing this is. This is a definition of a part. Inside this, it has two subparts, has one engine, 4 wheels, and then an interface. Now, those of you with SysML v2, you'll know that SysML v2, instead of connectors, we have connections, and interfaces are no longer like UML interfaces, they are connections between ports. Just like normal engineering interface control documents and whatnot are what's in the middle. SysML v2 interfaces are in the middle. So we've got an interface here for the drivetrain. So it's an interface usage called drive. Drivetrain is the interface definition, and it is between a drive port and a driven port. Right, so I'm going to start just showing that graphically, but really as I go on, I'm going to use the textual notation. It's just easier to put up and easier to generate for what we're going to be talking about. So this is a textual notation that directly corresponds to this. We've got a part depth for a car, the engine, 4 wheels, the drivetrain that connects the drive port to the driven port. And that means the 1 and the 2 here mean that this one engine is just connected to 2 out of 4 of those wheels. So that's SysML v2. What I want to point out is that we've got the same keywords here. These keywords are going to be important. When I say that's the kind of thing, well, we sort of know what a part is as an engineer. That's why we called it a part. We use the term interface in an engineering way. But what really is the meaning behind those things? Where do we define what those terms actually mean? I'm not going to go into a lot of detail about all the background of that. I could give you a whole nother talk on kernel semantics. Then you really would be rushing for the door. But what I do want to do is relate the basic idea that our systems library, the semantic library for SysML v2, basically defines what these terms mean. So this is spread over actually a number of library models. Actually, the systems library is not that big because it's based a lot on kernel, but it's got a lot of stuff in it. I've taken some key concepts and just put them together that relate to the model I just showed you. So I said, part definition, definition of a part. Well, what's a part? Well, we've got a concept in here of a part. It's kind of interesting because it is a bit circular because it's defined in SysML v2 itself. So we've got a part definition of a part. This is a part that is just a generic part. What do we know about a generic part? Well, I've just simplified it here. But what this says is that a part can have own ports. A port is another kind of concept here. And it turns out that a part is a kind of item. And an item can have sub-items and subparts. Now, where's the real semantics of this? Well, you notice that item specializes object. So let me put my little callouts here. Each kind of thing has a corresponding concept. And ultimately, this relates back to kernel. So the idea of an object is something in kernel. If you look at an object, it's a structural occurrence. An occurrence is something that occurs in space and time. And there is actually a huge semantic model of 4D relationships in space and time that is all pulled in here. So if you go back, what we're basically saying is that an item is a structural occurrence over time that can have space, that can have other items in it, and can have parts. How is a part distinguished from any other kind of item? Well, a part can have ports. It actually can also have performed behaviors and other things. And that starts giving you an idea of how we define these terms in the library. We've got here the idea of a connection that specializes the idea of an association from kernel. And then this specifically says a connection has a source and a target. That's actually a binary connection. We can have n-array connections, but don't worry about that. Nobody likes those anyway. So binary connection have a source and a target that can be anything, but an interface has to have, redefines those. So you have a source that's a target that are ports. Right, so this is just a very simple example that I could have said that without showing that and just described to you what parts and ports and interfaces are and how they're related. You know, a part can have ports and then an interface is a connection between two ports. That's the formalization. That is the vocabulary. Rather than me just saying it in English, that has formal meaning and relates back to the semantics, the kernel semantics in kernel. So how does that connect to the syntax I showed you? Well, it is through these keywords. So this is the piece that I showed you before. I put that in the context of a little bit more of the model here that talks about the drive port, that the engine and the wheels have ports. This is the definition of that drivetrain that says you can have 0 or 1 drive port connected to many potentially driven ports. It doesn't say how many, but here we have the connection from 1 engine port to 2 wheel ports, right? So that's my model. Well, here's the thing. Behind the scenes on this, there's a bunch of implied specializations of the library. We didn't want people to have to, modelers are people too, have to put in these explicitly. But this is where we get the semantics. When you say in SysML that you've got a part def engine, and you don't say anything else, right? When I said just this, what it means is that part def engine specializes part. And when I say that it has a port, that means that that subsets the own ports. That happens automatically in the tool. Now, it may seem trivial, but it has consequences because it means that you can do things like ask for the owned ports of an engine and you will get that port at runtime, when you do it at your analysis time, say. So it has consequences. It also means that you can specialize that. And in fact, that's what you're doing without thinking about it. You are specializing that semantic vocabulary every time you model in SysML v2. That's what it means. The SysML v2 syntax is basically providing you with semantic markers. That's what our syntax is. You could actually do this without all those keywords and just specialize things in the library. It would be semantically the same. All of the syntax, whether it's graphical or textual, is basically just to make it easier to pull in the semantic concepts from the library and make you think you're still doing something like SysML v1. All right, so let's now take that concept. Let's say now what we want to do is create a lot of different kinds of vehicles. All right, this is a little bit contrived, but I had to keep it simple for the talk. So what we're going to do is extract from this car model things that we might want to use to do other vehicles, which is most of it, but we have made some specific decisions here that this car, a car will have 1 engine and 4 wheels and 2 drive wheels. That's specific to that car. Other vehicles, 18-wheelers, motorcycles, they're all vehicles. Some may not even be wheeled vehicles, but we're going to stick with wheeled vehicles. So I'm going to create a vehicle library that maintains the idea that you have a drive port, that an engine has a port, a wheel has, this little symbol is conjugate, which means you flip in and out, that we've got the drivetrain interface. Now, that is the generic concept defined just like we had those concepts for our standard library. We're defining the concepts. We're going to say, when I talk about vehicles, I can talk about engines and wheels and drivetrains, and I can put that together to create a vehicle. There's a little bit more here that I hid earlier on, but it's going to be important as we go on, is that it also provides both definitions and base usages. So in SysML v1, a property was always a property of something. You couldn't talk about properties independently. You couldn't have a part property that wasn't in a block or a value property that wasn't in a block. Ontologically, you can talk about properties that are generic properties that could potentially be properties of anything until they're contextualized. And in ontological languages like OWL, that's straightforward. You separate the idea of properties and classes and concepts and then bring them together. We can do that too. And in fact, as we go forward, that provides the basis for providing usage level domain-specific concepts. So the pattern here when you're doing a library like this is not only to have this part def for engine, but also this base. And it has multiplicity 0 dot dot star because that's the most general. It really should also say non-unique on it because unique is unfortunately the default, but I didn't worry about that. So you can see these are paired up. I have an engine, engines, wheel, wheels, drivetrain, drivetrains. Then when I define a vehicle, what I'm saying is that a vehicle will have some number of engines, some number of wheels, and some number of drivetrains. All I've done, because I already have these usages here, is I've contextualized them. This redefinition just means that a vehicle will have its own set of engines. So there's this general concept of engines, and then for a vehicle, it will have its own set of engines, but each vehicle may have another set of engines and another set of wheels, and it can potentially have multiple drivetrains, driving different wheels in different ways. That's my concept. That's my library now of the concepts I'm going to use to create a vehicle. Oh, there's another one. I just said that. So this is now the car example re-expressed using the vehicle library, which basically means I just have left here the definition of the car. It specializes the vehicle. It has one engine, which subsets. Actually, that probably should be a redefines. Actually, it could be it depends if you want to extend this further. Let's say it's subsets engines. 4 wheels, which subsets the general concept of wheels. And then a drivetrain here, which is a subset of the drivetrains that you get from vehicle. So what we have here is that we're taking the base class, which is the concept of a vehicle, and then we are specializing the features from that context. So if I didn't do anything, it would just get inherited. But what I'm doing is saying that for a car, I only want to have one engine and 4 wheels, and 2 of those wheels specifically are going to be driven. But now I've got a template. Now it means if I go and define a motorcycle, I am also going to have engines and wheels and a drivetrain, but in that case, I'll restrict it to 2 wheels and one of which is driven in the drivetrain, etc. So I've got a general concept now, and I can create tools that allow me to talk about vehicles, wheeled vehicles with engines in general, and I can create a palette, for instance, that lets me drag and drop and whatnot. But I'm still thinking of this as using a SysML v2 library, which in many situations is fine. And when we use like quantities and units, that's where you think about it. You're pulling quantities and units from the library. When we use the shapes library, you're using shapes from the shape library. But if we want to really think of this as a domain-specific language, we want to make it more like what we do with SysML v2 and have some syntactic markers that allow us to have shorthands. Now, what we decided was we didn't want every SysML v2 tool to have to be a domain-specific language engineering tool. We may get there. That would be pretty cool when you could create whole new languages with whole new grammars and whole new syntax, concrete syntax. I think there will be tools like that, but we didn't want to require that out of the bat of every tool vendor to do that, because there are tools like that, and they are themselves very sophisticated tools. So instead, we have a capability for adding user-defined keywords, and it's really just a shorthand for doing what we're doing with the keyword concept in general. To set that up, however, I need to introduce the concept of metadata. So this is the metadata defined in order to allow me to use those shorthands. So metadata in general are user-definable model-level annotations of an element. So those are like stereotypes. And in fact, you can make them just syntactic. So you can create metadata that just has additional properties on them and use that to tag. And so we've got standard ones, like if you want to say there is an issue on this, or that this model element has some risk level or whatnot, you can just put that on there and just tag it and just have additional information in your model. This is semantic metadata. So semantic metadata links an element to a base type. Just like we said when you did a part def, it was linked to part in your library. We want to make that same linkage. So you can see what happens here on this metadata def for drive. I did these in a different order. But you see the base type is that drivetrains. That was from here, right? You remember we had engines and wheels and drivetrains. So what I've done when we get here is said, all right, I want to use this metadata. That metadata can annotate interface usages. That's why we had to define the usages of the library, because we want to annotate usages as drivetrains. So we tie to that usage. What this means when I tag something with this drive, I want to tag an interface usage and have it automatically be a kind of drivetrain. And similarly here for engine and wheel and vehicle. So it's just two things saying what kind of thing is annotated, and when I do the annotation, what kind of thing it is semantically. Annotated element is the syntax, base type is the semantics. Now that looks a bit complicated, but fortunately the user doesn't have to see this. The person defining the library sets this up, but it's pretty much just a table, a two-column table in a textual notation. When we go back to the car example, now we use this little hash on there for the user-defined keyword. That's how we get it added. You don't have to define the grammar. The existing textual notation and graphical notation says that when I put a hash on it, that is not a predefined keyword. Go look up that keyword, find the metadata for it, and apply the metadata. Here, so what I've done here is say, this is going to be a def, and I'm going to apply the vehicle metadata, and that application implies the specialization of the base type. So semantically, that's like what I said before, that this is a kind of vehicle. But now it is much closer to the syntactic concept we have in the SysML v2 itself. Similarly, we now say that the car is a vehicle. We've got a car engine, one engine, four wheels, and the interface. Now, there is still some, I don't know if they call them rough edges, but some compromises that people would start using this notice. You notice I actually left out here that this is a kind of part def, this is a part, but I had to put that this was an interface. And again, that is because we are still riding on top of the existing V2 concrete syntax grammar. Interface has a special notation, the connect to this to that, and the parser wouldn't know to use that unless you put in the interface keyword. So hold the questions till the end, and we can get back to them. There is, anyway, so right now, you can't quite completely, in all cases, hide the underlying grammar. That is something that we may be able to address as we go forward. There are some ideas now to reorganize the base grammar a little bit, but it does get, again, to the point of how far do you want V2 tools to go to really create domain-specific modeling languages, because as they get more sophisticated, it's going to be harder to keep the performance, it's going to be harder to keep the reliability, they're going to be bigger and more expensive, right? So there are trade-offs here, and that is something that we will see. This is a rather new kind of capability that we have, and we're going to need feedback from the community as we go to see how much more sophisticated this needs to be made, or if it's overkill already. So I wouldn't, that is basically the summary of what we're doing for language extension. I want to talk a little bit about how that is already being used. And probably the biggest user of them all is now the Unified Architecture Framework version 2. I think how many people have used UAF? Or at least know about it, right? It's used to develop architectural descriptions at the enterprise level. It's used across commercial, federal, military organizations now. It came out of DODAF and MODAF, but it's much more general than that. And people have used the Zachman framework. It can all fit into this. And it's an OMG standard. Dassault, Lockheed Martin, and Cozy were some of the leaders in originally creating it. It's ISO standard. Current version is 1.2. But work is ongoing. A lot of good work is ongoing with V2. Some of you may have been to the V2 or the UAF summit. I heard some about that yesterday. So I'm going to sum a little bit with courtesy of Aurelius. This is the basic idea with UAF V2 is they're actually still going to support V1. The idea is that there will still be a profile to support V1. So this is the basic meta model. Still a profile to support V1, but the interesting thing here is that V2 is going to be done with the V2 model libraries. There was a lot done in the UAF V1 to try to find ways to capture the semantics, a lot of special kinds of stereotypes and usage of things. What they're finding, which is very nice, is that a lot of what they had to try to work around or add to UML and V1 for UAF V1 is already there in V2. There's the time semantics is already there. The allocation semantics is already there. A lot of stuff is already there. The integration between behavior and structure is already there. So very much now they are using this metadata approach. And this is actually taken from the work that they're doing. This is examples of those metadata defs. It's exactly examples of a major effort really using these semantic metadata. Now, at one point, they talked about maybe just doing it as a library. So the best practice is always to start with the library because you need the library, you need the semantics. So on the other hand, UAF, they already had this big profile and all these stereotypes. So there's also well, we could just take the stereotypes and move those over as metadata. Do we need the metadata? Can we just use the library, or do we want to replicate what we have as stereotypes? As they worked on it, they realized, and Aurelius talked about this in his presentation, is you can't not use the metadata. Right? That is powerful for being able, for tools being able to deal with this as a domain-specific language. So the metadata concept is very important here for really being able to look at this as a DSML, but keeping the tie to the library. And this is an example. I just wanted to show that it's not all textual notation. This is an example of that, of using those metadata with the graphical notation, and you can see the hash is still here. Just like we had the keyword, the part def keyword here before, same thing. We have the keyword here, and we just put the hash in it to show that it is a user-defined keyword. Very consistent notation. Another example, which I also mentioned earlier in the day, is AADL, the Architecture Analysis and Design Language. This is an SEA standardized language used for safety critical embedded system, usually designing software to allow analysis and generation. It is a strongly typed language. It has standardized extensions of its own. Right now, the systems modeling community, the real-time embedded safety critical systems working group, that's a mouthful, and it's even harder to try to pronounce the acronym, Seidewitz. But they are also doing some really good work with the vision of merging SysML V2 and AADL to extend the principles of digital engineering to address safety critical systems and enabling end-to-end traceability. They are encoding their concepts in a SysML V2 kernel library. So this is an example of a part definition. Actually, here. This is an actual AADL, SysML v2 AADL example. This is from the standard library of parts and a standard library of attributes. They are considering whether or not also to use metadata, but the important thing is because AADL has analyzable semantics and executable semantics, one of the reasons people continue to use AADL and some of the safety critical community over doing V1 was because they could do the formal analysis in AADL. They couldn't do on V1. Now they can do it. And what they're trying to do here is replicate the domain-specific semantics that they need in the V2 library. Exactly a domain-specific language extension. This is another outside of the standards world. Some of you may be familiar with Arcadia and Capella, which was generally considered an alternative to V1 for systems engineering modeling. Working with Karen Ryan and Tony Kumar from Siemens, we took a hard look with Tallies, who is the originator of Capella. It is open source now. A hard look at, well, what is the relationship now of Capella, which is the tool, and Arcadia, which is the method, to SysML v2? What we found is a lot of the reasons that they did Capella, and they really was to support their Arcadia method. And a lot of the issues with V1 that we were also addressing in V2 were the reasons they created Arcadia, because V1 didn't support the method that they wanted for systems engineering. In particular, having component decomposition, what we call usage-based modeling. That was very important. One of the reasons it's important in V2 is because it was a problem in V1. The connection between behavior, the allocation of behavior to structure was difficult in V1. They had to address that in Capella. They addressed it in V2. When you then look at it, it's like, all right, can we replicate the semantics of Capella and support the Arcadia method with V2? The answer is actually very much yes. And we actually created, you can see here an example of this. Now, you can see it. You're not meant to have to read it. This is an actual model from Capella. It shows a structural decomposition with activities allocated in that structural decomposition. This is the equivalent SysML v2 that tries to duplicate that. And it is built on a library of Arcadia Capella concepts. One of the interesting things is, while they have a nice book describing Arcadia, and they have a tool Capella, there is nowhere a formal semantics, and the tool doesn't always seem to line up with the book. Our library, our SysML v2 library for Capella, actually was more the most formal semantics, I think, that had been defined for Capella and Arcadia to date. It wasn't 100% yet, but some of that is actually being used now for integration between Capella and SysML v2 tooling. And we presented this at an Arcadia IS last year. So that gives another example, and I will just conclude with that. SysML v2 is a general purpose modeling language, but it has powerful capabilities for domain-specific modeling. The concepts of metadata and model libraries replace the V1 concepts of stereotypes and profiles, but they're not a one-to-one replacement. The model libraries can be used to define domain-specific semantics, building on the existing semantic libraries that come with the language, and the metadata can then be used to annotate the model elements and tie them to the library-based types. This is already being used for standard domain-specific language development, and it allows me and you to do domain-specific modeling in your projects, organizations, and for our community. Thank you.
So Ed, we have seen over profiling of SysML v1 break interoperability, even if people were using the same tool in the same company, but they were using different SysML we won profiles. And a previous remark on a panel from Sandy was that industries, if they want to go down this route, need to agree on a standardized way of creating these specific DSLs. Right, Sandy? Yeah.
Sure.
So,
Sure, Daniel. Yeah, that's it. Uh-huh.
no, but I really think
Yeah,
it's
Daniel, we're good. No,
no, I think it's very important to stress this is beautiful, but be careful because it will break interoperability if you don't.
well, like anything else, and that's one of the issues, the domain-specific modeling languages. And I have had significant discussions with some of my friends in the programming language world about DSLs, because some of them say, oh, the best way to do it is for any problem, you define another DSL using the tool that I sell. And that you can end up at a company with 10, 100 different domain-specific languages. And even if they have the same common substrate, yeah, it can actually hurt communication across groups. One of the reasons to base it on a common substrate and base it on a common general purpose language is that you can at least always drop down into that general purpose language. But when people are used to using the specialized domain specific version, they sometimes forget that, oh, but in general, SysML v2 or whatnot is that way. So there is a couple things to help address this. And one is, you're right, we need best practices. And we're already developing that. And something that does need to get recorded as we go forward is, for instance, constructing your library with both definitions and parallel usages, how you use metadata, and setting it up in a consistent structure. The other thing is, though, one of the issues with the profiles is that there wasn't any formal semantics behind it. It was really hard to put in validation rules because you had to use OCL or something else that was outside the language itself. And even then, they weren't always validated. And there was no semantics. The tool couldn't check interoperability semantics. Again, if we do this right and teach people how to create semantic libraries, even if they aren't really super sophisticated, just define the basic vocabulary, that provides a basis for now tools actually doing integration and checking. That's a little bit more sophisticated than some tools do, but we already have tools doing more validation in V2. So I think your comment needs to be taken under advice, but I think we have a lot more opportunity to do it right. But it's not going to be perfect because people will get carried away with anything. Anytime they have a powerful capability, they'll get carried away.
I just have the feeling that there is very high demand from the industry, especially automotive, where I do most of this work, that the models are interchangeable across organizations. Yeah. And I just want to raise the comment that it's important. If you want to go down the DSL route, you have to standardize with your peers.
Yeah, and the other thing is, you mentioned, and that's true, you mentioned even within the same tools. So as a general concept, that's true. One of the things that was a problem also is that stereotype application was actually not in the abstract syntax for UML and SysML v1. There were reasons for that, but what it meant is that tools implemented it differently. There was not a clear conformance for that. The only way you could understand it was going to MOF or XMI. So it was almost impossible to do interchange across tools. Okay. Even if you're using the same tool, you have these issues, but at least we can now, with the metadata, cleanly interchange across tools.
Thanks, Ed. Chris?
So if you go back a few slides to where you were showing the hashtag stuff. So is that, and this is more,
this one, I forget which one it was.
That was the one, I think, yeah. So this is more of a technical question, but is this meta programming, aspect oriented programming, or meta aspect oriented programming, or something else?
Whatever you like.
I think we're going to have a semantics problem, Daniel.
So I actually have a term for it that I coined. It's called metasemantic programming, metasemantic modeling. So there was a book that I don't know if some of you know, but a while ago, called The Meta Object Protocol, written by Katsales, basically on how to extend Lisp within Lisp by making the internal mechanisms of effectively the Lisp interpreter available so that you could extend it and create your own extensions and macros. It turned out that while that was a wonderful idea, it didn't take off. It did influence aspect-oriented programming, which then had its own hype cycle. But a little while into this, I realized that what we were doing was basically elevating that basic idea of meta object protocol within specifically Common Lisp object system to this general concept of being able to do meta semantic extension. So instead of it just being, oh, I have objects that determine how my execution happens and I can open those up. We have semantic libraries that determine the meaning, but they're open. And the key thing that's like the meta object protocol is they're written in the same language. The reason the meta object protocol worked because it was Lisp and you could update the meta stuff in Lisp. Our meta semantics is actually at the same model level, so we can extend it at the model level. So that's what I call it.
So it is meta aspect oriented. Okay.
There is. It is always. So it's always meta someplace.
Yeah.
I never met a model
Okay.
I didn't like.
Thanks.
So I'm Mike Collins with APL. Quick question, how does SysML v2 handle queryable properties?
I guess what you mean. How does it handle?
So in other words, like for example, I can create, if I were in Cameo, for example, I could create a derived property spec where I could ask for it to give me an indirect relationship and populate it as a property.
Where you could create. So say that again. Where a derived property.
I could create a derived property spec where I could ask Cameo to say, okay, if this was a genealogy, for example, tell me who my mother is, and then tell me if my mother has a sister.
Yes.
And then I could create a property that says aunt, and it would populate that person based on the relationships.
Yes, we can do that very simply because we have the expression language built in. And you just bind it and you could say aunt equals mother.sister.
Okay.
Now you can even do that. That's why I paused a bit because of the previous question. We can actually even go to the meta level. So you could actually say, give me all the, take what I'm in, the owner of this feature, if it's a part, get me all owned members of that part syntactically that happen to also be part usages, and find me the one that has the name aunt, and then tell. So we can actually reflect into the meta level, query that, and actually traverse the model. So that's the meta capability, and that was actually used. I didn't get into it, but you notice a little meta here, because the base type has to point into the syntax, the meta level. But the simple capability of just doing derived property, which was never quite clear how to do that in UML and SysML v2 in a standard way, in v1 in a standard way, is really simple in v2 because you just say this equals that, and we have a full expression language, and you can just navigate your model.
Thank you, Ed.